Hello everyone, I am Dr. Shimpi Ralhan from Sri Shankaracharya Technical Campus, Bhilai. Welcome to the NPTEL course on Industrial Automation and Drives. Today we will explore the principles of electrical machines. We will look into the theoretical concepts and their practical applications. Electrical machines play a vital role in our lives, converting electrical energy into mechanical energy through motors or vice versa through generators. These machines are found everywhere, from the industrial equipment that powers manufacturing plants to the appliances in our homes and even the vehicles we drive. Here's what we will cover in today's lecture. What are electrical machines? Different types of machines including DC machines, AC machines and transformers. The basic concepts such as electromagnetism and the magnetic circuits. Now, if we look into it, that what an electrical machine is. An electrical machine is an electromagnetic system consisting of a magnetic circuit and an electric circuit coupled with each other. The magnetic circuit is made up of a stationary and a rotating magnetic member and a non-magnetic air gap to separate these two members. The electric circuit can be in form of one or several windings which are arranged to move relative to each other together with the magnetic members carrying them. For their operation, electrical machines depend on electromagnetic induction and utilize the electromotive forces or EMFs that are induced by the periodic variations in the magnetic field as the windings or the magnetic members are rotated. For this reason, electrical machines may be called electromagnetic. Let's begin with the different types of electrical machines. They can be broadly classified into two categories based on their structure, that is static machines and rotating machines. Further, they can be classified as DC machines, AC machines and transformers. DC machines are those that either generate or use direct current. A good example of DC machine would be a DC motor, which we often see in applications that require control of speed and torque. Another example you can say is DC generator, which is used in applications where stable voltage is needed without the fluctuations inherent in AC power. Depending on working of machine, we have, as just we discussed, we have generators and motors. Electric generators are machines which convert mechanical energy into electrical energy, and motors are machines which convert electrical energy into mechanical energy. This is a very basic definition which all of you know. So, transformers are simplest and most commonly used electromagnetic energy conversion device which converts alternating current at one voltage to alternating current at some other voltage, and the coils and core remain stationary relative to each other. The periodic variations in the magnetic field, they are essential for an EMF to be induced. So, the transformers are static machines. They either step up or step down voltage levels without changing the frequency. Since transformers operate on the same principles as generators and motors, depending on the action of a magnetic field to accomplish the change in voltage level, they are usually studied together with generators and motors. If we see now AC machines, we have induction motors, we have synchronous motors and AC generators or alternators. So, these together are most widely used AC machines. Now, if we see the very concept of the machine, the magnetic fields are the fundamental mechanism by which energy is converted from one form to another in all the machines, that is motors, generators and transformers. Four basic principles describe how magnetic fields are used in these devices. Number one, a current carrying wire produces a magnetic field in the area around it. Number two, a time changing magnetic field induces a voltage in a coil of wire if it passes through the coil. This is the very basis of transformer action. The third one is a current carrying wire in presence of a magnetic field has a force induced on it. This is the basis of motor action. The last one, a moving wire in the presence of a magnetic field has a voltage induced in it, and this forms the very basis of the generator action. Now let us see that how the production of the magnetic field occurs. The basic law governing the production of magnetic field by a current is Ampere's law. This law states that for any closed loop path, the sum of the length elements times the magnetic field in the direction of the length element is proportional to electric current that is enclosed by the loop. If you see the mathematical operation, it is the closed loop integral of H dot dl equals to I enclosed, where H is the magnetic field intensity produced by the current I and dl is a differential element of the length along the path of integration. So, the Ampere's law for the current carrying conductor can be seen from the figure. In simpler terms, Ampere's law helps us understand that when an electric current flows through a conductor, it generates a magnetic field around it. A current carrying coil produces magnetic field whose intensity is decided by the permeability of the medium through which the flux passes through. The figure shows a core with a coil of wire wrapped around one side with n turns in total. If the core is made up of iron or other similar metals which are known as ferromagnetic material, almost all the magnetic field generated by the current will stay within the core. So, when we apply Ampere's law, the path we consider for the calculation is the average or mean length L around the core. The total current within this path is given by the product of number of turns in current, because the wire loops around the path n times, each carrying a current I. Therefore, Ampere's law can be expressed as the product of H into L, which equals N into I. Here H is the magnitude of the magnetic field intensity vector H. Therefore, the magnitude or magnetic field intensity in the core due to the applied current is expressed as H equals Ni by L. The magnetic field intensity H can be thought of as how much effort a current is putting into creating a magnetic field. The actual strength of the magnetic field produced in the core also depends on the material of the core. The relationship between this magnetic field intensity H and the resulting magnetic flux density B, which measures the strength of magnetic field within the material, is given by B equals mu 0 H, where H is already we have seen magnetic field intensity, mu is the magnetic permeability of the material, B is the resulting magnetic flux density produced, and the expression is used throughout in the magnetic circuits. So, let us see the magnetic circuits in details. We see that current in a coil of wire wrapped around a core produces a magnetic flux in the core. This we can say is analogous to a voltage in an electric circuit producing a current flow. It is possible to define a magnetic circuit whose behavior is governed by equations analogous to those for an electric circuit. The magnetic circuit model of magnetic behavior is often used in the design of electric machines and transformers to simplify the complex design process. Let us see the basics which we should know before going into details of magnetic circuits. What is magnetic circuit? It is a closed path followed by magnetic lines of force. In the magnetic circuit, magnetic flux or magnetic lines of force, they start from a point and end at the same point after completing their path. A magnetic circuit is made up of magnetic materials having high permeability such as iron, soft steel, etc., which are known as your ferromagnetic materials. After seeing this, let us now discuss the basic terms which are associated with magnetic field and will be used quite often. The terms are magnetic flux denoted by phi, magnetic flux density denoted as B, permeability denoted as mu, magnetic field intensity H or magnetic field strength, reluctance S, magnetomotive force MMF. So, the number of magnetic lines of forces that set up in a magnetic circuit is known as magnetic flux. It is analogous to electric current I in the electric circuit and its SI unit is Weber. Next is magnetic flux density. At a point is the flux per unit area at right angles to the flux at that particular point. And SI unit of flux density is Weber per meter square. It is expressed as B equals phi upon A, where phi is the flux in Webers and A is the area in meters square. Next is permeability. So, we define permeability as the ability or ease with which the magnetic material forces the magnetic flux through a given medium. The flow of the flux produced by the magnet not only depends on the magnetic field strength, but it also depends on one important property, that is the magnetic material permeability. So, it is related to the medium in which the magnet is placed. The force exerted by one magnetic pole on the other depends on the medium in which magnets are placed. Permeability is expressed as the product of mu naught and mu r, where mu naught is the permeability, absolute permeability, and is given by 4 pi into 10 to the power minus 7, and mu r is equal to 1 in case of air. So, this constant plays a fundamental role in electromagnetism, particularly in the equations which describe the magnetic fields generated by currents. Next is magnetic intensity or magnetizing force H, also known as magnetic field strength. The magnetic intensity at a point in the magnetic field is the force acting on a unit north pole 1 Weber, that is 1 Weber placed at that point. The magnetic intensity is also defined as the amount of magnetomotive force per unit length of the magnetic circuit. It is expressed as the ratio of B and mu, and by Ampere's law we have seen that H can be written as the product of number of turns and current. The unit is ampere per meter, and this determines how a material responds to external magnetic field influencing the magnetic field inside the material. Then comes reluctance. The reluctance is the obstruction offered by a magnetic circuit to the magnetic flux. So, as in electric circuit there is resistance, similarly in the magnetic circuit there is reluctance. But if we see resistance in electrical circuit dissipates the electric energy, and reluctance in the magnetic circuit stores the magnetic energy. Its SI unit is ampere turns per Weber or Henry inverse. And here if we talk of reluctance, it is also a very crucial concept in designing the magnetic circuits such as transformers and inductors. The reluctance of the magnetic circuit is directly proportional to the length of the conductor and inversely proportional to the cross sectional area of the conductor. Thus, we can say that the reluctance depends on length of magnetic path, the cross sectional area, and also depends on the property of the material that we are using for the construction of the magnetic circuit. So, S is we use S to denote our reluctance, and it is expressed as L by A mu, or mu can be also written as mu naught into mu r, where L is the length of the magnetic path, mu is the permeability of the material, and A is the cross sectional area of the path. The reciprocal of the magnetic reluctance is magnetic permeance. It is a measure of a material's ability to conduct magnetic flux. It represents how easily a magnetic field can pass through a material or magnetic circuit. So, higher the permeance, the greater the magnetic field for a given magnetizing force. It is given as P equals 1 by S. The unit is Weber per ampere turn or Henry, and we can express also this as the ratio of mu A by L, where the mu is permeability, A is the area, and length is the L is the length of the magnetic path. Now let us see what magnetomotive force is. The current flows in an electric circuit due to the existence of electromotive force or EMF. Similarly, if we see the magnetic circuit, magnetomotive force or MMF is required to drive the magnetic flux in it. The magnetic pressure which sets up the magnetic flux in a magnetic circuit is called MMF. The SI unit of MMF is ampere turns, and you can see that the strength of the MMF in the inductive coil that is shown in the figure is equivalent to the product of current around the turns and the number of turns of the coil. It is expressed as F is equal to Ni. In order to study the magnetic circuits, we should know that how is the behavior of the ferromagnetic materials. Magnetic permeability, as you know, is given as B equals mu into H. It is observed that the permeability of the ferromagnetic materials is very high, that up to 6,000 times the permeability of the free space. Although the permeability is constant in free space, this is not true for iron and other ferromagnetic materials which are used in the construction of the electric machines. So, to understand how magnetic permeability behaves in a ferromagnetic material, we can gradually increase the direct current applied to the core, as you can see in the figure, starting from 0. As the current increases, we can plot the magnetic flux in the core against the magnetomotive force that produces it. This plot is known as saturation curve or magnetization curve, which shows that initially a small increase in MMF leads to a large increase in flux. However, after a certain point, further increases in MMF result in smaller increases in flux. Eventually, additional increase in MMF causes almost no change in flux, and this flat part of the curve is called saturation region, meaning the core is saturated. The steep part of the curve where flux increases rapidly is called the unsaturated region, meaning the core is unsaturated. This transition between the two regions is sometimes referred to as the knee of the curve. It is to be noted and is very important that the flux produced in the core is linearly related to the applied magnetomotive force in the unsaturated region only, and thereafter it approaches a constant value regardless of MMF in the saturated region. Another closely related plot is a plot of magnetic flux density B versus magnetizing intensity H. As H can be written as Ni by L, we can also replace the product of N into I by F by L, and phi is given by B into A. Thus, magnetizing intensity is directly proportional to MMF and magnetic flux density is directly proportional to flux for any given core. Therefore, the relationship between B and H has the same shape as the relationship between the flux and MMF. You can see both the curves which are shown. We have till now discussed how a magnetic field is created and its characteristics. Now, let us explore the different ways an existing magnetic field can influence its surroundings. For this, we have to understand electromagnetism, which is a fundamental aspect of physics that deals with the interaction between the electric currents and the magnetic fields. Electromagnetic induction is the process by which a change in the magnetic field in a conductor induces an EMF within the conductor. This very phenomena is fundamental to the operation of machines like generators and transformers, where energy conversion occurs through the interaction of magnetic fields and conductors. So, let us see the brief recap of electromagnetism principles. Electric fields are created by electric charges. The strength of the field is proportional to the charge and inversely proportional to the square of distance from the charge, given by the expression E equals k q by r square, where E is the electric field strength, q is the charge creating the electric field, r is the distance from the charge to the point of measurement, and k is the Coulomb's constant given by 8.99 into 10 to the power 9 Newton meter square per Coulomb square. So, the magnetic fields are the fields generated by moving electric charges or currents. A magnetic field exerts a force on other moving charges or magnetic materials, and the mathematical expression that describes the force exerted by magnetic field on moving charges is given as F equals Q V cross B. Here F is the force exerted on the moving charge, Q is the charge of the particle, V is the velocity vector of the particle, B is the magnetic field vector, and here cross denotes the cross product between the velocity vector and the magnetic field vector. So, this expression describes how a magnetic field exerts a force on the charged particle moving through it with the direction of the force given by the right hand rule. So, we have seen what is electric field and what is magnetic field. Now, the force experienced by a charge moving in an electric and magnetic field both is described by the Lorentz force law, which can be expressed as F is equal to Q E plus Q into V cross B, which we have seen in the previous slides. When a conductor moves in a magnetic field, an EMF is generated. When it carries current in magnetic field, a force is produced. Both of these effects may be deduced from one of the most fundamental principles that is discovered by Michael Faraday in 1831, that is principle of electromagnetism. And this provides the basis for number of devices in which conductors move freely in a magnetic field. The first law states that a changing magnetic field induced an electromagnetic force in a conductor, or whenever a conductor is placed in a varying magnetic field, an EMF is induced. Likewise, if the conductor circuit is closed, a current is induced, which is called induced current. And the second law is the induced voltage in a circuit is proportional to the rate of change in the flux over time of the magnetic flux through that circuit, and given by E equals d by dt of phi with a negative sign, where E is the voltage induced in the turn of the coil and phi is the flux passing through the turn. If a coil has n number of turns and if the same flux passes through all of them, then the voltage induced across the whole coil is given as E equals minus n d by dt of phi, with all the symbols having their usual meaning. The minus sign in the equation is an expression of Lenz's law here. The Lenz's law states that the direction of the voltage buildup in the coil is such that if the coil ends were short circuited, it would produce current that would cause a flux opposing the original flux change. Since the induced voltage opposes the change that causes it, a minus sign is included in the equation. So, we can say that the negative sign indicates that the EMF works against the change in magnetic flux. If a magnetic field through the loop of wire is increasing, the induced current will create a magnetic field that opposes this increase. Similarly, if the magnetic field is decreasing, the induced current will try to maintain the field by opposing the decrease. So, we can say that the Lenz's law is the refinement of Faraday's law that gives the direction of the induced EMF and current once we have the magnitude. Lenz's law is reflected in the formula of the Faraday's law with minus or the negative sign. Hence, we can note here that the magnitude of induced EMF is given by Faraday's law and the direction is given by Lenz's law. Now, the Maxwell's corkscrew rule, also known as Maxwell's right hand screw rule, is a tool used in electromagnetism to determine the direction of the magnetic field relative to the direction of electric current. According to this rule, if you imagine a right-handed corkscrew or screw being rotated in the direction of the electric current, the direction in which the screw advances, or you can say tightens, it represents the direction of the magnetic field lines around the conductor. This rule is very much essential for understanding the relationship between current and magnetic fields in various applications such as electromagnets and motors. Another significant effect of a magnetic field on its surrounding is that it creates the force on wire carrying a current within the field. The idea is shown in the figure where a conductor is placed in a uniform magnetic field with a flux density B and is directed into the page. The conductor is L meters long and carries a current of I amperes. So, the force induced on the conductor is expressed as F equals I into L cross B, where I is the magnitude of current in wire, L is the length of wire with direction of I defined to be in direction of current flow, B is the magnetic flux density vector, and the direction of the force is given by the right hand rule, which states that if the index finger of the right hand points in the direction of vector I, middle finger points in the direction of flux density B, then the thumb points in the direction of the resultant force on the wire, and the magnitude of the force is expressed as F equals BIL sin theta, where theta is the angle between wire and the flux density vector. Now, understanding what causes induced EMF and its different types is important in studying electrical machines further. So, the requirement is not only linking the coil with the flux. The main thing is if we want to induce some EMF, the flux should change after linking with the coil. If there is no change of flux, there is no induced EMF in the coil. So, it is very important to note that the basic requirement to induce EMF is magnetic field, set of conductors and relative variation in space or time between magnetic field and set of conductors. Now, if we see the first requirement, magnetic field, then flux is to be produced, and there are two principles sources of flux, that is permanent magnet and electromagnet. The basic source of flux is permanent magnet. Here the flux cannot be controlled, as you can see. In order to have control on the machine in terms of say speed, flux needs to be controlled. Therefore, electromagnets are preferred with winding and a DC voltage source across it known as excitation. Excitation is essentially DC because it produces fixed polarity. We have come to the end of our lecture. So, just have a recap. We have discussed static and rotating machines and different laws behind them. Also, we have seen the different types of induced EMF used in machines and the magnetic circuits and the various terms associated with them. All the above discussions are important for designing and operation of electric machines such as transformers, generators and motors, which we will be studying in the forthcoming lectures. Thank you very much.